Hello, everyone. So I just got back from the International Worm meeting, which might sound kind of funny, but is actually a really big conference in my field. To be precise, it's like thousands of scientists coming from like dozens of countries all over the world to get together and talk about science, geek out, and give presentations. And we actually usually have like a big party to end it all off with like a DJ and open bar, and so it's a lot of fun. But anyways, so I ended up giving a talk. It was a short one, but it basically summarizes the work that I'll be publishing soon in the lead up to my thesis. And so, yeah, I thought I would share that with you guys here. And yeah, here, let me know what you think.
So our next speaker is from Baylor College, and we're going to be hearing about how NUC1 exonucleases acts in the lysosomes.
All right. Okay, cool. Here we go. Good morning, everyone. I'm Jonathan. And so today I'm going to go over some of the results that our lab has obtained in our efforts to determine whether there's any validity to an alternative model of NUC1 that's been published. Where did they click? Oh, here we go. Okay, so first it's important to understand that every cell in our body gets recycled on a regular basis. And the phagocytic cell corpse recycling process is a multi-step process that involves the formation and fusion of different specialized vesicles like lysosomes and phagosomes. Oh, it's not working. Okay, that's okay, I can just use the... When any step in this process is defective, it can cause a number of serious problems. For example, when mutations occur in the enzymes that are necessary for degrading DNA, this can lead to several different autoimmune disorders. And one of these enzymes is called NUC1. It's the C. elegans homolog of mammalian DNase 2, and as such, it's a lysosomal resident enzyme that functions optimally in an acidic environment. It was shown originally by the Zhao-Chung Wang lab, I believe, that it was lysosomal resident, and then in our lab we've also verified that. So we've known for several decades that NUC1 is necessary for degrading DNA, and the earliest epistatic analysis showed that it acts downstream of phagocytosis. However, some more recent publications have suggested that there may be a cell autonomous function for NUC1. So these results were based largely on what's called tunnel staining methods. And the interpretation of those results were proposing that DNA fragmentation was happening prior to engulfment by a phagocytic cell. But to us, it didn't make a lot of sense. So we were wondering whether the methods were being applied appropriately and whether the mechanisms required for such a function really made any kind of sense either. So we decided to test for ourselves whether we could find any evidence for a cell autonomous function. So we ultimately have two major questions we wanted to address. The first being whether phagocytosis is necessary for NUC1's function, and the second being if we could find any cell autonomous functions at all. So in the Zhou lab, we use primarily time-lapse fluorescence microscopy. Because we work with the awesome organism C. elegans, there's a number of programmed cell death events that we can follow throughout embryonic development. And the way that we do that is by putting some embryos on a microscope slide, lining it up under the microscope, and then taking some images along the z-axis over a specified interval of time. And this is what that looks like under the microscope. So we can see here, in this case, we're tracking, I need to switch to the cursor. In this case, we're tracking the cell corpse CM. And I don't know how to switch back to the cursor.
If you click the pencil looking button.
Yeah, but, okay, cool. There we go. Okay, so we're also using an mCherry tagged histone marker in this case. And we can see that that marker gets degraded along with the cell corpse. All right, I gotta pick it up a little bit. Oop. Okay, so because Hedgecock and Solston showed that NUC1 is necessary for DNA degradation, we wanted to use the NUC1 null allele to test whether our marker is reasonable for tracking DNA degradation. And as we can see in the NUC1 null background, our marker fails to be degraded along with the DNA. So this suggests that our model is reasonable for tracking DNA degradation. And additionally, we can measure the diameter of the mCherry signal over time across several replicates, plot it in a graph like this, and that allows us to do a more quantitative form of analysis. Using these methods, we wanted to test whether phagocytic engulfment is necessary for NUC1's function. To do that, we use a SED5 null allele. So SED5 is important for phagocytic engulfment and cytoskeletal rearrangement. But importantly, our analysis shows that even in the SED5 null background, most cell corpses still get engulfed. So because of that, we can only analyze or determine whether a cell corpse has been engulfed after an imaging session has been completed. I have two examples of embryos where we track the cell corpse CM and its clearance. And in the example on the left, we can see that the DNA actually gets degraded, just like in the wild type background. In the example on the right, when we track the cell corpse DNA, we see that it fails to be degraded, and the cell corpse itself actually moves around a lot more, which for unengulfed cell corpses, that's pretty common. They move around a lot and will often get completely ejected from the embryo. Okay, cool. So these results suggest that phagocytic engulfment is necessary for NUC1's function. We next wanted to test whether lysosomal delivery of NUC1 to phagosomes is necessary for it to function. To do that, or to test that, we use the RAB7 null allele. RAB7 is a small GTPase that's necessary for fusion of lysosomes with other vesicles like phagosomes. And so repeating our assay in the RAB7 null background, we can see that the DNA fails to be degraded, suggesting that lysosomal delivery via phagolysosomal fusion is necessary for NUC1's function. To test this a little bit further, we decided to do a rescue experiment in phagocytic cells specifically. So expressing RAB7 just in the engulfing cells, we can see that this actually rescues the DNA clearance defect. And when we compare wild type to the RAB7 null and the rescue, we can see that the clearance defect is rescued, but just slightly delayed relative to wild type. And then further expanding on this assay a little bit, we decided to track NUC1 localization in phagocytic cells specifically by using the phagocytic cell promoter. And we can see that NUC1 localizes in lysosomes on the surface of phagosomes after the nascent phagosome is formed, and then it gets delivered to the lumen of the phagosome via phagolysosomal fusion. Okay, so this raised a couple of questions for us. Because we see that NUC1 is active in phagocytic cells, and that's exactly what we expect, we wondered if NUC1 specifically derived from phagocytic cells is sufficient for NUC1's function in degrading cell corpse DNA. In other words, whether apoptotic cell-derived NUC1 is necessary at all. Okay, so to test that, we did a phagocytic cell-specific rescue of NUC1, and we saw, doing that, a complete rescue of the cell corpse DNA clearance phenotype. Okay, so then finally we wanted to test whether NUC1 localizes in apoptotic cell corpse nuclei prior to engulfment. And to do that, we generated a strain that expresses an mCherry tagged NUC1 along with a GFP tagged nucleoporin. And then in that strain, we test the NUC1 localization in apoptotic cells from the moment they're born until they're completely degraded inside phagolysosomes. And I have a small snippet of an example time strip here where we can compare NUC1 localization in a fully mature phagolysosome, or at least a maturing phagolysosome, at the 12-minute time point here. And you can see there's a lot of enrichment there. But at the 0 time point, which is what we consider engulfment to happen, we don't see any. And that suggests that there's no accumulation of NUC1 prior to engulfment. And indeed, when I've looked at prior time points, again, going all the way back to when the apoptotic cells are born, I don't see any evidence of NUC1 localization. And we can compare that also to non-apoptotic cells. So when we look in the nucleus of a cell that we don't see undergoing apoptosis, we also do not see any NUC1, which is a good thing. Okay, so our results suggest that phagocytic engulfment and phagolysosomal delivery of NUC1 is necessary for NUC1's function, but that apoptotic cell-derived NUC1 is not necessary for cell corpse DNA clearance. All right, and then in conclusion, we see no evidence of any cell-autonomous functions for NUC1. And importantly, even if NUC1 were delivered to apoptotic cell nuclei, we suspect that it wouldn't be functional because it's not an acidic environment. And the studies that were based on tunnel staining results that interpreted those results to suggest the cell autonomous functions, we think were overly reliant on the idea that engulfment mutants completely block engulfment. And our results, even in different engulfment mutant backgrounds, suggest the opposite, actually, that we actually see most cell corpses are still engulfed. So With that, I'd like to thank the organizers and all of you for giving me the chance to go over this work, and I will open things up for questions. I was going to say either really good or really bad.
So most of what you showed us was in the embryo. Did you look at the expression and the localization of NUC1 in adults as well?
I haven't. Oh yeah, the question, sorry, was whether we looked at NUC1 localization in adults as well instead of just in embryos. So we generally just do imaging, or well, we don't just do imaging in embryos, but we often prefer to do imaging in embryos because we can track cells really easily, individual cells. Whereas like after the 1.5-fold embryonic stage, the cells move around a lot more. Although I think gonadal cells are probably a reasonable model to use for that too. But I haven't specifically looked at that. So great question though. We still have about a minute, so plenty of time to.
Sorry, I'm just waking up. So,
Oh, no, blame you.
The cell needs NUC1, but do you know subcellularly exactly where? Because it looks sort of perinuclear. So do you know subcellularly what's going on in the engulfing cell in NUC1?
So it does appear that it's perinuclear, right? The lysosomes, and then from what I've seen, it appears that the phagosomes, when they're nascently formed, kind of like will. So we've seen images. I forget who published that. Was it Barth? I forget. The phagosomes will reach out and grab lysosomes and bring them in, or the lysosomes will be transported towards a perinuclear location to facilitate fusion as they mature. So it depends on the cell specifically, because sometimes the nucleus is kind of close to the plasma membrane and they can fuse there. But oftentimes you see some kind of movement either towards the nuclear location or lysosomes being dragged towards the plasma membrane. So, yeah.
Wonderful. Thank you so much.